Hold a piece of Iceland spar up to a cloudy sky today, and something extraordinary happens. The crystal splits light. Two images appear where there should be one. Rotate it slowly, and those images shift, brighten, dim. Find the exact point where they match in intensity, and you've just done something Viking navigators may have done 1,000 years ago. You've found the sun. Without a compass, without GPS, without even being able to see the sky. This is the story of the Viking Sunstone, a navigational crystal so effective it helped Norse sailors cross the North Atlantic, find Iceland, reach Greenland, and touch the shores of North America 5 centuries before Columbus. And then, somehow, it vanished from history so completely that for hundreds of years, scholars assumed it was a myth. It wasn't. It's the late 9th century. A Viking longship pushes west from Norway into open ocean. No landmarks. No coastline, just grey water in every direction and a sky thick with cloud. This is where most ancient sailors stopped. The Mediterranean traders hugged coastlines. The Arab merchants followed established routes with clear skies and familiar stars. But the Norse went somewhere else entirely. Into the North Atlantic, one of the most hostile stretches of water on Earth. Storms without warning, fog that swallows everything, weeks at sea with no reference point. And yet they navigated it, accurately, repeatedly. They reached Iceland around 870 AD, Greenland by 985, the coast of North America, which they called Vinland, by around 1000 AD. Eric the Red, Leif Erikson, names attached to journeys that shouldn't have been possible without modern instruments. So how did they do it? For centuries, historians pointed to their skill with the stars, their knowledge of ocean currents, wave patterns, bird behavior, whale migration routes. All real, all used. But stars require a clear night sky. The North Atlantic doesn't often offer one. There had to be something else. The answer may have been sitting in their hands the whole time. The first written reference to a sunstone appears in a 13th century Norse saga. The Ráðulfs That, an Icelandic tale, describes King Olaf asking a man named Sigurd to determine where the sun is on a heavily overcast day. Sigurd produces a Sólarsteinn, a sunstone, holds it up, and identifies the sun's position through the cloud. The king checks it against his own knowledge. Sigurd is right. Historians read this and argued for centuries about what the sunstone actually was. Some said it was a metaphor. Some said it was mythology dressed as history. Some said Norse sailors simply made educated guesses and occasionally got lucky. Then in 2013, researchers diving on a sunken English warship called the Alderney, which went down in 1592, found something unexpected in the ship's navigation equipment. A rough, rectangular crystal, pale, almost translucent. Iceland Spar, calcite crystal, optical grade, on an English ship, sailing more than 5 centuries after the Vikings, being used for navigation. That find changed everything. To understand why the sunstone works, you need to understand something about light that the Vikings almost certainly didn't know in scientific terms, but had clearly figured out in practical ones. Sunlight, as it passes through the atmosphere, becomes polarized. The light waves align in a specific pattern relative to the sun's position. This polarization happens even when the sun is hidden behind clouds, even at sunrise and sunset when the sun is below the horizon, even in conditions where no other navigational method would work. The human eye cannot detect polarized light, but Iceland Spar can. Iceland Spar is a naturally occurring form of calcite crystal found abundantly in Iceland, which the Norse knew well. When you look through it, it splits light into 2 beams due to a property called birefringence, double refraction, 2 images where there should be one. Here's the critical part. When you rotate the crystal while looking at a uniform patch of bright sky, the 2 images change in brightness. At one specific angle, they match exactly, equal brightness. That angle directly reveals the direction of polarized light and therefore reveals where the sun is, whether you can see it or not. It's physics, elegant, precise, repeatable physics. And a skilled navigator who knew what to look for could use it in seconds. The case for the sunstone didn't rest on the Alderney find alone. In 2011, researchers at the University of Rennes published a study in the Proceedings of the Royal Society, examining exactly how accurate sunstone navigation could be. They modeled Viking voyages from Norway to Greenland. They factored in the cloud cover typical of North Atlantic conditions. They calculated how often a navigator would need to take a sunstone reading to stay on course. The results were striking. Even under heavily overcast skies, with sunstone readings taken every 3 hours, a Viking navigator could maintain a course accurate enough to find Greenland reliably. Not sometimes, reliably. They tested it further. During the spring and autumn equinoxes, when Viking voyages were most common, the accuracy improved even more. The sun's polarization pattern is strongest at those times of year. The tool worked. It worked extraordinarily well. A follow-up study in 2013 from the same research group showed that navigators, using Iceland Spar in simulated overcast conditions, could determine the sun's position to within a few degrees. That's comparable to early magnetic compasses. Better, in some conditions, because a magnetic compass has its own failure modes. Magnetic anomalies, ion interference, proximity to other metal instruments. The sunstone has none of those problems. It just needs light, any light. So if the sunstone worked this well, why did it vanish? This is where the story gets complicated and darker. The magnetic compass reached Europe from China via Arab traders sometime in the 12th century. By the 13th century, it was in widespread use among European sailors, and it had one overwhelming advantage over the sunstone. It was easier. No skill required, no practice, no learning to read the subtle shift in brightness between two overlapping images. Just a needle pointing north, every time, in any conditions. The compass democratized navigation. You didn't need a specialist anymore. You didn't need someone who had spent years learning the craft of reading light through crystal. You needed a box with a magnetized needle and you were done. Viking culture was already changing by this point. The age of the great Norse voyages was winding down. Greenland's Norse settlements were struggling. The Vinland colony had been abandoned. The longships were being replaced by merchant vessels built for cargo, not speed. The knowledge of the sunstone was almost certainly oral, passed from navigator to apprentice, embedded in practice, not in writing. When the need for it faded, when the compass made it redundant, there was no one left with a reason to teach it. And so it was forgotten, not dramatically, not in a single moment of loss, just quietly, gradually, the way practical knowledge always disappears when the conditions that made it necessary stop existing. The sagas mentioned it, but sagas were stories. Scholars treated the reference as legend. The Alderney crystal reopened the question in ways that couldn't be ignored. Its presence on a 16th century English warship suggests the knowledge didn't die with the Vikings. It survived, transformed, passed into European maritime culture without anyone necessarily knowing or caring where it originally came from. English navigators in the Elizabethan age may have been using a technique that Norse sailors pioneered 6 centuries earlier. After the Alderney find, researchers went back to museum collections and found other crystals that had been sitting in storage, mislabeled or unidentified, for decades. Some appeared to match the optical properties needed for sunstone navigation. Some had been found near Viking archaeological sites. The physical evidence was accumulating. In 2018, a paper published in Royal Society Open Science went further. Researchers built a computational model of exactly how a sunstone would perform under the range of sky conditions typical of North Atlantic crossings. They factored in the sun's position at different latitudes and times of year. They calculated error margins. Their conclusion was unambiguous. A navigator using Iceland's Spar could cross from Norway to Greenland with a positional error of less than 50 miles. In the open ocean, in any weather. 50 miles. In an age without any other instrument capable of that accuracy. There's something else that makes this story remarkable. The Vikings didn't just accidentally stumble onto Iceland's Spar. Iceland's Spar comes from Iceland. The Norse reached Iceland around 870 AD, earlier than most historical accounts once assumed. Some researchers believe they may have settled there, partly because the island was a reliable source of this navigation crystal. Think about what that means. The tool that allowed them to cross the Atlantic may have come from the first significant landmass they reached in the Atlantic. Iceland gave them the crystal. The crystal helped them find Greenland. Greenland gave them the base to reach North America. one discovery building on another, a chain of navigation stretching thousands of miles, anchored in a pale rectangle of calcite you could hold in one hand. The Sunstone story is also a story about what we choose to dismiss. For most of the 20th century, the historical consensus was that the Norse sagas describing advanced navigation techniques were romanticized exaggerations. Interesting, colorful, not to be taken literally. Scholars who suggested otherwise were treated with skepticism. It took physical evidence, a crystal pulled from a shipwreck, to force the reassessment. This happens more often than historians like to admit. Ancient peoples are credited with ingenuity after the fact, once the physical proof appears. Before that, the default assumption is often that they must have been doing something simpler, that they couldn't have known what modern science now confirms they somehow knew. The Vikings couldn't have explained birefringence. They wouldn't have used that word. They didn't have a theory of polarized light. But they had the crystal. They had the sky. They had generations of accumulated practical knowledge. And they had the Atlantic. That was enough. Today, Iceland's Spar is studied in optics laboratories. It's used in scientific instruments, high-precision cameras, laser equipment. Military targeting systems use principles of light polarization that trace directly back to the same physics a Norse navigator exploited in the 9th century with a rough piece of crystal and an overcast sky. The Jorvik Viking Center in York keeps the memory of Norse innovation alive. The National Museum of Denmark holds artifacts from the Greenland settlements. Researchers at universities across Europe continue publishing studies, refining what we know about sunstone accuracy and distribution. And if you go to Iceland today, you can still find Iceland's Spar. You can hold a piece up to the sky, watch it split the light, rotate it slowly until the two images match. In that moment, you're doing exactly what a Viking navigator did, standing at the edge of the known world, reading light through stone, finding the sun in a sky that offers no sun to see. They crossed an ocean with this, 5 centuries before anyone else thought it was possible. That's not myth. That's not legend dressed as history. That's one of the most remarkable acts of practical human ingenuity in the ancient world, hiding in plain sight inside a crystal that sat unrecognized in museum drawers for decades. The Sunstone was real, the voyages were real, and the knowledge, once lost, has been found again. As always, we'll see you in the past.